Today's lecture is just a collection of examples taking derivatives involving inverse trig functions. So we'll just call them all examples. Everything I'm doing today involves taking the derivative of something. So I'm going to start with y equals tan inverse of radical x. So let me start by taking dy over dx. Now remember, the derivative of arctan or tan inverse is 1 over 1 plus x squared. So I'm going to get 1 over 1 plus, it's not x though that's in those parentheses, it's the square root of x. So instead of an x, I'll put a square root of x. Of course, the formula says that you're supposed to square it when you're done. Now that's not all there is to it. Since this is not just x inside of here, I have to use the chain rule and take the derivative of radical x. Instead of radical x, if you don't mind, I'm going to write it as x to the 1/2 power. I find those easier. Powers are easier than radicals any day. This part right here just simplifies to 1 over 1 plus x times, and then the derivative of x to the 1/2 is 1/2 x to the negative 1/2. And that's perfectly fine with me. There's no reason to do anything else with it if you don't want to. Let's try y equals arcsine of x squared plus 1. Well, the derivative of arcsine is 1 over the square root of 1 minus x squared. But instead of x being squared, I'm going to put the entire x squared plus 1 inside of that box. So I'll have x squared plus 1 squared. And then as before, I need to take the derivative of x squared plus 1 because of the chain rule. I don't see any simplifying that I'd really want to do on this radical, so I'll just go ahead and leave it like that. But the other piece, the derivative of x squared plus 1 is simply 2x. The next one is y equals arcsecant inverse of, I said arcsecant inverse, but I actually mean arcsec or sec inverse. ln x, take the derivative, dy over dx. These were among the most complicated of them all. The derivative of arcsec was 1 over the absolute value of x times the square root of x squared minus 1. So let me get that stuff in there first. Instead of an x, I'm going to put an ln x where I see it. Don't forget the absolute value is part of the formula. Then the square root, instead of x squared minus 1, I'm going to have ln squared of x minus 1. Notice I put that 2 on there. And times the derivative of ln of x. And so I don't see a lot that I can do. I don't see anything that I can do with the first part of this, so I'll just rewrite it. And I can't really do anything with ln squared x minus 1. And finally, the derivative of ln of x is 1 over x. Another example. Y equals tan inverse of cos inverse of x. So the derivative, d over dx, equals dy over dx, dy over dx. The first thing I'm going to process is arctan, so I get 1 over 1 plus something squared. Well, what is that thing that goes there? Well, that's the stuff that's inside the parentheses, cos inverse. But then because of the chain rule, I have to multiply by the derivative of cos inverse of x. And I don't see anything to change down here. I'll tell you one thing, that students that really do not understand the nature of an inverse function will do stuff like this. What have they done? Well, they don't understand what they're doing, first of all. Second of all, they applied the power rule to this. So that, I think saying that is enough. Let me get it out of here. I don't want its ugliness to harm the example anymore. So take it out. I'm just going to leave it. There really is no simplifying of that part. So I have 1 plus cos inverse squared. Cos inverse, the derivative of it is negative 1 over the square root of 1 minus x squared. Remember, it's simply the negative of the derivative of arc sine. Let's try the next example. Y equals e to the cotan inverse of 1 plus x cosine of x. Alright, well, the derivative of y with respect to x, the derivative of e to the x is e to the x. So I got to write all this stuff down. So I have e to the cotan inverse of 1 plus x cosine of x. But then the chain rule tells us that we need to multiply everything by the derivative of this stuff inside the parentheses. So d over dx of 1 plus x times cosine of x. I put that dot there to remind myself to use the product rule for that piece. And the e part is just going to bring down each time e to the cotangent inverse of 1 plus x cosine of x. The derivative of 1 just goes away, so I'm really working on just the derivative of x times cosine of x. So you'll want to use the product rule for that. The derivative of x is 1, derivative of cosine of x, or leave cosine of x alone. Then I'll leave x alone, but take the derivative of cosine, which is negative sine of x. And that's perfectly fine for an answer. You can tidy it up if you want. I wouldn't bother. Y equals the square root of tan inverse of x all over the cubed root of x to the fourth. All right, first thing I'm going to do is get rid of all these silly radical signs and change this to powers. So instead of that, I'm going to have y equals tan inverse of x all over x to the 4/3, and that is to the 1/2 power. So the outermost function is to the 1/2 power. So when I take the derivative, dy over dx, first thing I'll get is 1/2, leave the stuff alone inside right now, tan inverse of x divided by x to the 4/3. That's to the negative 1/2 power, but now I got to take the derivative of the stuff in the parentheses. That's the tan inverse of x divided by x to the 4/3. Now I'll just be operating with the rest of this throughout the rest of the problem. This part here is going to stay put. So we have 1/2 tan inverse of x all over x to the 4/3 to the negative 1/2. For this piece here, I'm going to use the quotient rule. So the quotient rule says the first thing I take the derivative is the top part. So I'll have a 1 over 1 plus x squared there. Leave the denominator alone, x to the 4/3. Now minus, this time leave the numerator alone, but take the derivative of the denominator. And the derivative down here is 4/3 x to the 1/3. Oh, I completely forgot my denominator here. I should have x to the 4/3 squared. And play with it if you want. I wouldn't. So moving on. This one, I've been saving up this one. I'm a little excited about. Let's do y equals cos inverse of x to the sine inverse of x. And you remember, one of the first things you want to do with these, there's a couple ways of doing these, but probably the easiest is to rewrite y in this fashion. E to the sine inverse x ln cos inverse of x. That way, when I take the derivative, I'm going to get this stuff again, because e to whatever, e to the x, the derivative of e to the x is e to the x. So I'll get that again. E to the sine inverse of x times ln cos inverse of x. Now, by the chain rule, I take the derivative of what was in the exponent. That was sine inverse of x times ln cosine inverse of x. Inside of there, that's a basic, that's just a product rule in there. This part here, I'm going to rewrite it as the original function again, or the way the function was originally written. So I have cos inverse of x to the arc sine of x times, now I'll do the product rule. The derivative of inverse sine is 1 over the square root of 1 minus x squared. Leave ln cos inverse of x alone, plus, now this time we're going to leave sine inverse alone, but the derivative of ln of cos inverse of x is 1 over cos inverse of x. But see, this cos inverse of x is inside of the natural log. 1 over x is the derivative of ln of x. So I still need to attach on this piece the derivative of cos inverse of x. So let me write it here. I don't think it's such a good idea to try to do too much at once. Take your time on these things. And so this equals cosine inverse of x to the sine inverse of x times 1 over the square root of 1 minus x squared times ln cos inverse of x. I should have had parentheses. I'm going to put brackets around this. It's so big. I forgot them. Plus sine inverse. I'm going to combine that at least. So we'll have sine inverse of x all over cosine inverse of x times. Now, if you try to simplify this in any way, you are gravely mistaken. Just to even think you can simplify it is a mistake. So don't bother with it. You can't write it as tangent inverse or anything like that. And this last piece, the derivative of cos inverse of x is negative 1 over the square root of 1 minus x squared. And there you go. That ugly old thing. And I could do a little, I might, if I were writing this, if if I were writing official answers for a test or something, I might combine these fractions. I might combine this stuff all into one, whatever. One last example, and we're going to have a little bit more to do this time. I want to determine an equation for the tangent line to f of x equals inverse sine of x times inverse tan of x at x equals radical 2 over 2. So solution. Well, what do we need? In order to get any kind of a tangent line, we need a point and a slope. So the point's easy enough. Let me get, for the point, I'll plug in that x value. We have f of radical 2 over 2 equals arc sine of radical 2 over 2 and times tan inverse of radical 2 over 2. Well, you should know that arc sine of radical 2 over 2 is pi over 4. Unfortunately, there is no such number for tan inverse of radical 2 over 2. So I'll just leave it like that. I'm not going to use a decimal or anything like that. That's just going to be my point. So I'll reference that in a minute. For the slope, I need to take the derivative. So f prime of x equals, I'm going to use the product rule, take the derivative of sine inverse first. So I'll have 1 over the square root of 1 minus x squared times tan inverse of x plus inverse sine of x times the derivative of arctan, 1 over 1 plus x squared. So now if I want the slope, I have to plug in radical 2 over 2. So f prime of radical 2 over 2 equals 1 over the square root of 1 minus radical 2 over 2 squared. If you know, that's just 1/2, by the way, times arctangent of radical 2 over 2 plus arc sine of radical 2 over 2 times 1 over 1 plus radical 2 over 2 squared. So let me put in the numbers that I do know. Radical 2 over 2, if you square it, you get 1/2. So I get 1 over 1, the square root of 1 minus 1/2 times arctangent of radical 2 over 2. That number I do not know. I do know that arc sine of radical 2 over 2 is pi over 4. And I know the last piece will equal 1 over 1 plus 1/2. Now, since I'm going to be using this in a problem, I'm going to simplify this as much as I possibly can. 1 minus 1/2 down here will give us the square root of 1/2, which will simplify to be radical 2 arctan radical 2 over 2 plus pi over 4 times, I have 1 over 3/2, or better yet, let me call that 2/3. And then I can do just the slightest bit of simplifying here. So we end up with radical 2 arctangent of radical 2 over 2 plus pi over 6. So that'll be my m. So now we're ready. The point was radical 2 over 2. The y value wasn't so good. Oh yeah, it's not so bad. This is the point that I got earlier. Pi over 4 times tan inverse radical 2 over 2. And there's my slope. So the m I already have. So we're going to do y minus y0 equals m times x minus x0. Y minus, so my y0 is this stuff, pi over 4 arctangent of radical 2 over 2 equals the m is all of this stuff. So let's get it in there. Radical 2 arctan radical 2 over 2 plus pi over 6. That is m. And x was, the x naught was radical 2 over 2. And I am happy with this particular format. Now, if I actually want to check this, graph it, and see if it gives me the answer, to write it in a notation that my computer will understand, I'll have to add this to both sides. It'll understand all this stuff. That's not a problem. Okay, I've taken the liberty of graphing the original function with this tangent line all at once. I simply added this stuff to this point right here is the one, the tangent point. That was, the x part was radical 2 over 2, comma, and the y part, what was that again? What was the point? Pi over 4 tan inverse radical 2 over 2. So that's the point there. Of course, this graph here is f of x equals arcsine x times arctangent of x. And that line down there, of course, is this line right here. So I'll just take this whole thing here and tell you that that refers to the straight line. And so this tells me that my computations were correct. That line certainly looks tangent right at that particular spot. Slope is good and everything like that. So we'll call it quits there.